Hey guys, welcome back to my channel and this is Varun Tahin. So in the previous sessions, we have spoken about least square approximation, where it is used and why we use such technique. We have also touched based upon eigenvectors and eigenvalues and understood how do we calculate it given a matrix. Now, if you guys have not seen that video, I would recommend to take a step back and check that video first, as this video is a continuation of eigenvectors and eigenvalues where we will see some examples. So you can directly click on the top right corner of the screen to navigate to that video. Now in today's session, our agenda is to continue discussing some examples and problems related to eigenvalues and eigenvectors, and lastly see how eigen decomposition of matrix works. So let's start. Now first we will quickly recap what we have learned in the previous video about the steps to find eigenvectors and eigenvalues given a matrix. So let's say that if we have a matrix A, we have to first form lambda I and then subtract lambda I from A, forming equation A minus lambda I, and then equate its determinant to 0 to find the lambda. And then in the next step, using the lambda or eigenvalue found in the step 1, we will find the eigenvector from equation AV equals to lambda V. Now let's solve some examples in order to be very clear how do we calculate eigenvalues and eigenvectors. So we have been given this matrix A which has values -1, 0, 0, 1, and we have to calculate the eigenvectors and eigenvalues for this. Now based on our understanding, what we will do as the first step is put everything into the equation determinant A minus lambda I equals to 0, right? Or in other words, we can say determinant of -1 minus lambda, 0, 0 and 1 minus lambda equals to 0. So here what we have done is we have calculated the lambda I. Okay, so lambda I will be lambda into the identity matrix, right? Which will be lambda 0, 0 and lambda. So if we subtract A by this, we will get this matrix, right? And when we calculate the determinant of it, we have to equate it to 0, right? As the first step. Now since this is the case, we will find the determinant. So determinant of it will be AD minus BC, right? Where this is the first element, which is A, this is D, this is B and this is C. So if we multiply -1 minus lambda by 1 minus lambda and then subtract 0 into 0, which is 0, right? We have to equate it to 0. And since this is the case, therefore lambda will be either equal to -1 or 1. So we have got the eigenvalues of the matrix A. Now as the next step, what we have to do is we have to equate AV equals to lambda V, right? Now what we will do as the next step is for lambda equals to -1, we have to calculate what is V, right? So let's assume, okay, let's assume V as A and B vector, right? Now putting A and V in this equation, we will get -1, 0, 0, 1, A, B equals to -1 into A, B, right? Now when we multiply this, we will get minus A, B equals to minus A minus B on the right side. And since this is the case, when we equate the left hand side to the right hand side, we can say minus A equals to minus A and B equals to minus B. And can you infer when this will be true? This will be true only when B is equals to 0, right? Because in any other case, B will not be equal to minus B, right? It's only in the case of B becoming as 0 that we can say that B equals to minus B. So the eigenvector here becomes A and 0 for lambda equals to -1, right? And in other words, we can say that all the vectors of the x-axis are the eigenvectors of this transformation. Now in the next step, keeping the lambda as 1, we have to compute AV equals to lambda V, right? Now as A is -1, 0, 0, 1 and V is AB, lambda is 1 and V is again AB, then we can say that minus AB equals to AB, right? So in this case, minus A is equals to A and B is equals to B. So here this is only true when A is equals to 0. Just as we have found the previous equation and calculated B. right? Now here the eigenvector will be 0 and b, right? Now in short, we can say that we have got a0 as the first eigenvector, okay? So a0 as the first eigenvector and 0b as the second eigenvector, right? And we can put here different values for it, right? So saying 0, 1 and 1, 0 as the eigenvector also holds true, and saying 10, 0 and 0 minus 123 also holds true in this case. Now why we have said like this as to a and b can take any values? It is because of the reason that in this case all the vectors on the y-axis are eigenvectors with the eigenvalue 1, and in this case all the vectors on the x-axis are eigenvectors with the eigenvalue -1. We have to note that eigenvectors are usually reported in the normalized form. That is, though there are an infinite number of vectors that lie on the x-axis, conventionally we would report the eigenvector 1, 0. Similarly, the second eigenvector as 0, 1, but it will be not incorrect to say that 10, 0 and 0, minus 123 are also the eigenvectors of this matrix. Now we can do all this exercise in Python also to calculate the eigenvalues and eigenvectors for the same matrix. And you will be surprised to know that calculating in Python is way much easier than calculating it manually, as we will have various methods inside the NumPy library to do it automatically for us. Okay, so in this case we have the same matrix, and let's see how do we do it in Python. So first we will form the array, okay, by np dot array, where np is nothing but the NumPy alias, and here we will have the array in the form of -1, 0, 0, 1, right? And we can straight away do np dot linalg, which is the linear algebra utility inside the NumPy, and do dot eig to calculate the eigenvalue and eigenvector for this matrix. So what it will do is it will return us a tuple where C is the array of the eigenvalues and V is the matrix with the eigenvectors as the column. Okay, and at last we can print these two, right? So print C and print V, and this will automatically do all of the stuff for us. Now that we have understood how we calculate values for eigenvalues and eigenvectors, let's move on to the next topic, which is Eigen decomposition of a matrix. So this topic is similar to the topic we have studied in maths when we were in school, and the topic was called as prime factorization, wherein we will divide the number as the product of the prime numbers. So similarly here, if we have been given a matrix A, we can decompose it with an equation QE Q prime, where Q is a matrix whose each column is an eigenvector of A, and E is a diagonal matrix whose diagonal entries are eigenvalues of A. Now let's understand this with the help of example. So let's say that we have a matrix A represented by 2, 0, 0, 3, and we have to decompose it. So we already know how to calculate the eigenvalues and eigenvectors given a matrix. So we can do this for this matrix also. And here, as we have the diagonal elements only, the calculation is easy for us. So the eigenvalue here becomes 2, 3, and eigenvectors here become 1, 0 and 0, 1, as we have also seen in the previous example. Now if we want to decompose it in the form of QE Q prime, we can recall that Q was a matrix whose each column is an eigenvector of A. Thus Q will become 1, 0, 0, 1 as a combination of these vectors, and E is a diagonal matrix whose diagonal entries are eigenvalues of A, right? So it will be identical to the matrix in the question, which is 2, 0, 0, 3, right? So this way we can decompose any matrix by calculating the eigenvalues and eigenvectors of it. Now it is easy to see how decomposition is possible. So if we consider a 2 into 2 matrix A with eigenvectors V1 and V2 and the corresponding eigenvalues as lambda 1 and lambda 2, we know that AV1 equals to lambda V1 and AV2 equals to lambda V2. Now let's do a little matrix trick and arrange the eigenvectors V1 and V2 as the column vectors in new 2 into 2 matrix Q. Okay, so here Q will become V1, V2, right? Or in short, V11, V12 and V21, V22. Now we will also create another diagonal matrix with the eigenvalues as the diagonal entries. Okay, so here this E will become lambda 1, 0, 0, lambda 2. And we will notice that we can write two equations 1 and 2 in a compact form in one matrix equation, that is AQ equals to QE, right? And if this is true, since AQ equals to A into V1 V2, and we can further evaluate the value of A by multiplying each side by Q inverse. Okay, so the final equation we will have will be A equals to QE Q inverse. Hence we have proved that A can be decomposed in this form. So that will be all for today, guys. We from next session onwards will be learning calculus, so please stay tuned. Until then, guys, please do support by subscribing to my channel and liking the videos if you think that these material is helpful, and don't forget to hit the bell icon if you don't want to miss any future updates. I will be seeing you soon in the next session. Until then, keep learning and inspiring others. Thanks and take care.